The motions of the planets are nearly circular orbits, so it shouldn't be too surprising that gravity shows up in a chapter discussing rotational motion. You may recall that if we had an object close to the surface of the Earth, its weight was going to be the mass of the object times the acceleration due to gravity, and also that the gravitational potential energy was equal to mgy, where the y is the height above the surface of the Earth or above the tabletop, or exactly whatever reference you want to use. However, this was the near the surface approximation for potential energy. An excellent approximation for the motions of projectiles and other objects close to the surface of the Earth, but it's really not going to assist us with planetary motion or spaceships going on out into the solar system or anything like that. For that, we need the more full-blown theory of gravity, the Newtonian theory. We're going to stop well short of Einstein's general theory of relativity. Anyway, let's consider then now the entire Earth, the center of the Earth, and an object that's located not close to the surface of the Earth necessarily. So here's an object on out there somewhere, has a mass m. If this is indeed the Earth, we could say its mass is the mass of the Earth. And suppose that the distance from the center of the Earth out to that mass, cheat a little bit there, is r. Well, it turns out then the gravitational potential energy for that object is given by a formula that's very similar to Newton's law of gravity. It is actually equal to, there's the g, the universal gravitational constant, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, I think. And then the mass of the Earth times the mass of the object that's out in space, and divided by the distance between them, r. It's almost a reflex with Newton's law of gravity to make an r squared, but in the potential energy it is indeed just r, and it turns out it's awfully convenient to, in a way, measure the height down from infinitely far away. That's not exactly the story, but actually in this formula there's a negative sign that appears. So the gravitational potential energy with the full Newtonian theory is the negative of g times the mass of the Earth, mass of the object divided by the distance between them. And if the objects aren't the Earth and some other mass, if the objects were m1 and m2, just to make it more general, then in the product it would be not just me times m, but m1 times m2. In any case, what can we do with this? Well, it turns out we can do exactly the same sort of thing that we did in our chapter on energy. We can look at the conservation of energy, or in particular the conservation of mechanical energy. If we have a time initial and a time final, we have the Earth and the object at one distance. So that could be our initial, mass of the object, mass of the Earth, and maybe it's moving with some speed, v initial. And then later, well, maybe it's spiraling in, gotten closer to the Earth, should be moving faster now. We'd have v final, and the distance here is r final. Still have the mass of the little object, mass of the Earth. And then the total energy for that object is going to be its kinetic energy. Well, let's work up to it. The mechanical energy initial is going to equal the mechanical energy final. But the mechanical energy is coming from the motion of the object with mass m. So there's going to be that kinetic energy initial and that kinetic energy final, plus the gravitational potential energy of the object. I know it's gravitational, so I'm not going to write the subscript g, but the initial gravitational potential energy of the object, plus over here the final gravitational potential energy of the object. And then we can just fill in the kinetic energy, 1/2 mv squared. So here's 1/2 v initial squared. On the other side, 1/2 mv final squared. But then the gravitational potential energy, because it has that negative sign, we can put that in as a subtraction. And we have the g, the mass of the Earth, the mass of the object divided by the r initial. And on the other side, the big G, the mass of the Earth, the mass of the object, and divided by the r final. So it's the repeating concept, conservation of energy. If all the energy is mechanical, you can do the conservation of mechanical energy. It's also kind of nice, though. This really is free fall motion. And once again, it turns out that focusing on just the single object moving in the neighborhood of the Earth, the mass of that object appears in every term as a factor. And so if we were to divide both sides by the mass, the little mass, it would cancel out. And we could write our equation as 1/2 v initial squared minus g, the mass of the Earth, divided by the r initial, and that's going to equal the same thing, but with the final values appearing. So that really is probably a good equation as a starting point, although the thinking process and getting there is a very nice process. I encourage you to go through that and make sense out of it if possible. Also in this section, it discusses the idea of escape speed. And the escape speed, well, if you want to escape from planet Earth, that is the minimum speed needed so that if you could send an object up with that speed, it would just keep going forever. Most things go up, come back down. Here's a case where it has such a great speed that it goes up and it just never manages to turn back around and come back down. Here, though, we can go through the discussion if we wish. The object has to get infinitely far away so that the final position is infinity in essence, and dividing by infinity is going to cancel out one of the terms. Also, the initial position of the object, well, if it's launched or sent off from the surface of the Earth, the r initial would be the radius of the Earth. And we can make use of those ideas. One more here. The final speed, it just barely gets out there infinitely far away. We can take the final speed to be 0. And then solve. And in fact, if we go through the algebra, not difficult to do. But here, I'm just going to put the formula. The escape speed, if you want to get away from planet Earth, is going to be the square root of 2 times the universal gravitational constant times the mass of the Earth divided by the radius of the Earth. And we could plug in and actually, if you want to try that, wonderful, ends up being about 11.2 kilometers per second, although most of us don't really think in terms of kilometers per second. So if we convert that to miles per hour, that's about 25,000 miles per hour. Has to go pretty fast to totally escape from the Earth. And we also have to cheat. We'll send things up on rockets, and it's not till it leaves the Earth's atmosphere that it really has to get up to that escape speed. If we try to make it go too fast while still in the atmosphere, friction is just going to, burn up the system. The air resistance is going to destroy the rocket or whatever we're sending up. In any case, 25,000 miles per hour may seem considerable, and it is a lot, don't get me wrong, but it turns out it's really only about double or maybe a little bit more the speed that's needed to put a satellite up in orbit around the Earth. So that's really kind of remarkable. We can send something up that orbits the Earth, but if we send it up twice as fast, it can just keep going forever. It will escape from the Earth, escape from the solar system, and no one's ever going to see it again, I suspect.